So we're back. I didn't have to take that call. Sorry. We are now okay. So we were what were we? We're looking at quotient groups. It's like modulus, but for groups, quotient groups. So a group G is a set equipped with a binary operation like multiplication or addition that satisfies closure. So a subgroup H that is itself a group under the same operation. And cosets for any element G that belongs to G and the subgroup H, the left coset is the set GH such that a GH element where H belongs to H. Okay, that's what's called left coset, I guess, because G is on the left. I don't know. Right cosets are defined similarly, but we'll focus on left cosets here. Cosets partition G into disjoint sets of the same size as H, like equivalence classes. Wait. It partitions G into disjoint sets. Cosets. So for an element G and in group G, and then and a given subgroup H, the left coset is the set of all GH elements where H belongs to. Oh, okay, yes. So essentially, you're saying for each element of G, then you have like so of course GH, and where G is a specific element of G of the G group, then you have all these different. Okay, I get it. So you have all these different subsets which are the same size of H, but then they are disjoint because they all have like one small G attached to it. Okay. Yeah. Okay. Yeah. A normal subgroup is a special type of subgroup where for every G and H, the conjugate GH. G inverse is also in H. It ensures left and right cosets coincide, which is crucial for the quotient to work. Oh, quotient subgroups can only be formed. I don't understand that, but okay. The quotient groups can only be formed using normal subgroups. Regular subgroups won't do because the operation wouldn't be well defined otherwise. Okay, well, I'm not going to get into that right now, but we'll just assume it's true. So given a group G and a normal subgroup H, the quotient group G over H. Oh, it's red modular. Okay, G modular H or G over H. Okay, that's okay. It's defined as the set of all left cosets. Okay, the set of all left cosets. So this means GH. Okay. Of H in G, that is, yeah, okay, the set of all left cosets. The operation for two cosets GH and KH, their product is the product of G and K. Okay. Why is it well defined? Because H is normal, the choice of representative G and K doesn't matter. If you pick different elements from the same cosets, you get the same resulting coset. The identity element, the inverse, the order size of G is to deform mod out by H, meaning all elements of H are treated as neo-identities. I guess what this does is it just picks this H as a subset, and then it's just basically saying we're just gonna look at that. So how do I have this concept? Start with the idea of equivalence relationships. Yeah, I mean it's the same. It's modular. It's just modular, right? I don't think I need to understand the normal subgroup stuff for now in order to solve the problem. But it's just modular. So what you're saying is, let's see if I can be a bit visual. So what you're saying is, let's say you have elements of your group, right? I don't know, or we just think about sets. Maybe that makes it easier. You just have elements of sets. And then you pick a few. So this is your set, and then these elements can operate with each other and satisfy all the properties and whatnot. Now you go and switch to red, and then say, look, we're gonna pick up this subgroup, right? And we're gonna ignore everything else in here, right? Because essentially now you have this concept of so you have now the concept of the left coset being for example, if I'm gonna give, let's say I'm gonna give this guy a name, like this is gonna say an A, right? And these are just gonna be 1, 2, and 3. So this coset thing is basically you kind of grab these, right? You kind of grab these. It's like A is paired with each of the red elements, and that's your left coset, and then you can do that with every single other white element, and so you have all the different cosets. But I guess what it allows you to do is basically it's a modulus. So you're just focusing on those on those three elements because they already just kind of represent the behavior of the set, of the group, of the bigger group. I guess that's what, because that's what happens with modulo, right? So with modulo you have like 1, 2, 3, like with modulo 3, and then basically everything else that comes in is just mapped to 1, 2, and 3, right? So if 4 is mapped to 1, 5 is mapped to 2, and so on and so forth. So you basically just doing 1, 2, 3, 1, 2. So you can go and get, and then you can go and under this definition you can like say, okay, so what is like 3 plus 1? Well, 3 plus 1 is 4, but that maps to 1. So in that modulo concept, 3 plus 1 equals 1, right? And it's kind of the same thing here. So what you're saying is whatever the operation of that set is, how can I get out of the, I keep forgetting, I think TT, yeah, exactly. So whenever you peek like and say, now I'm working on these, right? So, and let's say the operation is like a dot, because that's what that's maybe bad here, but that's what they do, right? So if I take 1 dot 3, right, the result of this operation, which actually might be outside of this 1, 2, 3 subgroup, it's gonna be, let's imagine that it turns out to be this element here, right? But again, this element, it's gonna be, because you've defined cosets, and that's going to be a coset for that element as well. Essentially, it's going to be whatever you attached it to, I guess. It's going to be, let's call these X. So it's going to be some sort of like X3, right? Let's assume that's multiplication, right? I think that's what's happening here. So it's like you're using, I mean, I don't know. I really don't know, because I really don't know how explicit you are with this, but like mentally, I think that's essentially what's being defined here, right? It's the concept of modulo. It's the concept of modulo, but like with groups. That's all fine. So what this means is, okay, but what does it mean C3 times C3, or C3 squared? Because then we need to understand what is that? Like, is that S over these equals C3? Is that what they're trying to say, right? So So first of all, what is C3 times C3? All right. All good. Thanks. Let me ask something else. What is C3 and what is C3 times C3 in group theory? Let's now kind of zoom in here. So we zoom in like the definition of C3 squared, right? And let's revisit that definition so we understand those two groups. And then how do we make that quotient group out of these? Just to make sure it's a C3. We can ask I wonder what type of software would you use to kind of aid yourself in that? Like, do you use something like SymPy, or do you use anything like to do like mathematical proofs? Okay, so it's a cyclic group. C, I guess, stands for cyclic. Cyclic group 3, often written as C3 or something just like C3. Denotes a cyclic group of order 3. This is the smallest non-trivial cyclic group after C2 and is a fundamental building block in the classification of finite groups. It has exactly 3 elements. It's a cyclic group. Okay, so it's generated by a single element A such that A cubed equals E, and E is the identity. So the elements are E, A, and A squared. Okay? So this is the cyclic group. It's isomorphic to Z over 3Z, integers modulo 3 under addition, with the operation I plus J mod 3. Doesn't matter, this is a concrete example. The group of rotations of an equilateral triangle, 0, 120, 240. I guess it's something that basically have 3 elements: an identity, and like an element A, and an element A squared, which means you're doing something twice. But the thing is cyclic 3, so this means these are, I guess, operations or things that when you do them 3 times, you go back to the identity. You can do it 1 time, 2 times, 3 times. That's why you have 0, 120, and 240, because you've got a rotation of 120 degrees. If you apply it twice, you have 240 degrees, and if you apply a third one, then you go back to 0. And yeah, okay, so that's what C3 is. The direct product, what is direct product in this case? Give me a second, guys. Okay, so the direct product, or direct sum in additive notation, I don't know what that means in this case, of 2 copies of C3. It constructs a larger group by combining the 2 groups component-wise. Okay. It is a well consists of pairs GH, where GH belong to C3. Okay, so you kind of have 2 groups. Yeah, but how do you construct these? So for what? It joins rotations in 2 independent dimensions modulo 3. Interesting. It's kind of like adding another dimension to it. It's one of 2 groups of order 9. The other is C9, which is a cyclic, has elements of order 9. In this case, it's if C3 is all the elements such that 3 times such that like A squared, A cube is the identity, and then you have another copy, B such that B cube is the identity, then this is basically all the pairs of elements, okay, A and B such that A cube and B cube are equal. A cube equals B cube, which equals E, and A times B equals B times A. So if you apply A and then B, is the same as applying B and then A. So, oh, look at these. So these subgroups often appear in, yeah, that's a little messed up because it's kind of like taken from a previous thing up there that I asked, I guess. Computations involving this, let me know. So these group, first of all, is there any software or library or like Python library to work with group theory? Because I'd be willing to explore that a bit more and understand elements. It's not cyclic. Now, what is this telling us? This is telling us that, so we understand what C3 is easy to understand. C3 squared is a little more abstract, right? Because, okay, now you have a group that is defined by yeah, it's like adding, I mean, it helps to think of it as adding dimensions. Because what I like about the dimensionality thing is the following. Let's go back here and refresh, right? Let's think of this rotation concept. So there was this concept of what we just read of like rotating 0 degrees, 120. Crap, man. I'll just do it. Thanks. So rotating 0 degrees, 120, and 240, right? But let's say now you just like think of a set where you're like in 2 dimensions. That would be like the x-axis. And then you have the same. Then you have the same 0, 120, and 240 on the y-axis, and you're thinking of a system that kind of like is described along these two. You know, it fulfills those properties. Like individually, each of these thing is a C3 group, and then together, if you apply a rotation here first and then a rotation in the y-axis, or vice versa, is the same, right? So that, as per this definition, makes sense. As per this definition here, makes sense. It's a nice, I think it's a nice example, right? But the way you were building this is you're just pairing both, right? I'm not so sure where they take that from, though. Because obviously that's a cube and a b cube, exactly. So how do you get to that, though? Because if it's going to consist of pairs GH, where G and H both belong to C3, to a C3 group. So with the operation defined component-wise, the operation is defined component-wise. So that's what the direct product says, right? So G1 H1 G2 H2 is basically G1 G1 H1 H1, and that kind of gives you the next element. So that's saying, like, for example, A and B and A squared and B squared. I guess you maybe can derive it from here. So that's maybe not too obvious. I need to build more intuition around these, though. But if I'm looking at this definition, it kind of makes sense. I can understand. It's not too abstract, actually, if you think about these. Yeah, that's the isomorph. If the example in here, vector space over F3 of dimension 2. So examples in context. In the answer, like a 2D grid over module 3. No. Okay. But how does this help with understanding these? So we understood these, and now I need to understand, I need to go back to these and do the quotient group, but I think I don't have time for that. I think I'm gonna have to put that for another video. I just wanted, let me just put in here, so general software for computational group theory. For more advanced and standalone work, dedicated computer algebra systems, Excel in, first I thought there would be, no, okay, wait. Python library, SymPy, a popular symbolic mathematics combinatorics module with tools for group theory such as permutation groups, finite permutation groups. Okay, PyGroup, integrated Python module. Okay, PyGroup. So there's something like this that exists. PyGroup. PyGroup. Group theory in math. Homepage. Three years ago. Two forks, Rainbow Dreamer, PyGroup, README. That's all what the README says. Awesome. I'm not so sure. This is a module written for groups and sets in terms of mathematics. Oh. SymPy. So what can you do with in SymPy with geeks? Why there's no direct link to SymPy? SymPy. So SymPy and documentation group. Combinatorics in group constructors, number of groups, group name groups, number fields, number of groups, permutation groups, gallows groups. So you define groups. Give me Python code to compute a quotient group. Given, assume we have the two groups already defined in variables. I guess that's something you do, right? Like that's I'd like to build more intuition around these, but you know, at some point in time, you just have to do these, I guess. All right, guys, I have to stop the video. Implementing manually. Isn't there any software for group theory? Okay, I can't wait until I see the answer. I'm ready to go, but I'll let you know in the next video what happened there. Because what I want to do is these. I want to basically, yeah. I guess I need to be able to code these. I just want to prove that this is correct, and then I want to, from I want to find a tool to actually work on group theory like this, and then induce possible non-trivial action of. Okay, so the next step is basically understand the action of these on D being defined like that. To be honest, it's a little tricky because it seems like C3s and C2s are like rather simple groups, and so this should be kind of more straightforward. But anyway, we're still stuck here in the first part where we're trying to understand the definition of S, like D times S, or S on D, and the action. And that's, I mean, that's how you define G, because we need to get to the definition of G so that we can understand first and tackle like how many blocks does KG have. Maybe a quick question: what are blocks? K be a large enough field? So if K is a field let me ask Grok one thing. So if K is a field and G is a group in group theory, what is KG and what are blocks of KG? Because that's like, I think from a structural perspective of the problem, that's what I'm missing to understand. That's what it's saying, right? So we have G, which is basically a group. Then we have K, which is a large enough field. And I don't know, what is a field? The field has characteristic. And the question is how many blocks does KG have? So that's what we want to answer, right? Group algebra. So in group theory and algebra, if K is a field and G is a group, then KG denotes a group algebra. Okay. Or a group ring. When K is a ring, but here it's a field. Okay. If J over K. This is a fundamental construction that combines the group structure of G with the vector space structure of over K. Okay, no idea, but that's like next level. So there's a vector space, blah, blah, and that's like an algebra. Algebra structure, KG is equipped with a multiplication that extends the group multiplication in G, making associative in algebra over K, specifically for two elements. So blocks of KG. Blocks arise in the modular representation theory of finite groups, particularly when K is an algebraic closed field. The blocks of KG are the indecomposable two-sided ideals B such that KG that gets deeper and deeper and deeper. Whoa. Okay, that's gonna be a very, very difficult one. Ooh, but it's yeah, I think it touches a lot of interesting. Can I ask one thing? I'm gonna stop. So I don't know if Grok is able to do that. Like, looking at the conversations in this project, can you build me a graph of the high-level concepts that I have been exploring? Let's see what it does. See you in the next video, guys.